Hey, so welcome back, everyone. So let's start with a few announcements. So I was, hopefully you all got the grades for the quiz. If not, you should probably tell me. I have them in my office. I forgot to grade them, I forgot to bring them. They're all in 3 piles unstapled, so we need to staple them first. So hopefully I'll have those back on Wednesday to return to people, or you can stop by my office at some point. So let's see. So for homework 5, it's not due for a couple of weeks still. There was a small typo in there that I've corrected in blue. There was a apostrophe, which is doing a transpose that was not needed to be there. And I just found out, I haven't fixed it yet, that I have some old data sets up there for X, at least for the X and Y data set. If you use the commands in there, it's not going to work because the dimensions aren't right. So I may have posted them correctly originally and then I overwrote them or something. I'm not sure, but I'll try and correct this after class. But it should, if the dimensions are not right, well then just sorry, I'll post the right data sets soon. All right, and hopefully I think I went through all. So I went through all the reports, the intermediate reports, and I tried. So I think I assigned all the grades and gave comments to everyone. I think I usually post a reply to all the group, but sometimes I forgot. So if you didn't get a comment, then you should check with your group members, and there's probably some comment on Canvas. If you didn't get a grade, that probably means I didn't get an intermediate report. There was a couple of those. So if that's the case, and I should have gotten one, you haven't gotten a grade, please let me know. Okay. And if you have more questions on my comments, please, it's probably better to email me or to come to my office hours than to reply in the comments, because I get lots of notifications from Canvas, and if it's a comment on a grade, I don't always check those. So email is better for that, or in person. Okay. So that the topic of today is broad, is noise in data. Okay. So we're going to try and explain to you what is noise. You probably have some idea of what noise is, but I'll try and kind of paint it in more of a coherent picture. And then how do you deal with noise? And so, kind of, noise is something that you often don't like to talk about, but you also always talk about, right? If there was, the point of data mining is to find kind of inherent structure that's in data, and if there wasn't any noise, these problems would be really, really easy, actually. So even though we haven't talked maybe about it explicitly all the time, this is really what's driving what's going on, in that we have to deal with this noise in some way. And so kind of a fairly basic assumption, which is not always the case for what we're thinking about, but for most settings, and I'll try and distinguish this a few times, is that you have some data X, and this is usually like the input that we want to analyze this, and what we want to find is some model that is a fit of this data. Maybe this would be a model of X, but this X is where we start, right, with the data, but it's not where the start of the process. There's often some distribution, say mu, that the data is coming from. Maybe this is like the real world, right? So we start from the real world. We somehow, data gets gathered. It gets put into our computers somehow, and then we build some model some model of the data. But this conversion from the real world into the data is, can be noisy. So this is plus some noise gets added on in this process in some way. And there's also often some implicit assumptions, and we'll use this a little bit today, is that this data is coming IID. This is not always true, but is often the case. And often, especially in statistics, it's a very common assumption. And this drives a lot of data mining and machine learning models are either explicitly or implicitly influenced by this assumption, this IID assumption. Okay. So before I move on, what does IID mean? So, yeah, so this means independently and identically distributed. So, so who's never seen this definition before? Oh, good. So that means you've had a proper probability class or statistics class. So when I was at this stage, when I was a junior graduate, it wasn't until I had been in grad school for 3 or 4 years before I figured out what this meant. Right? I'd read papers and stuff, and I'd seen this. I'm like, what does that mean? And it's hard to find. You could type IID into Google, it wouldn't tell you anything before. So
you used the term earlier this semester.
Okay. Oh well, good. All right. All right. So who had not heard it before the start of the semester? Okay. Good. So there's nothing to feel ashamed about that. But so just to review what this means is it means that each of the data points in our data set, if it's independent, means that we assume that the probability that one existed had nothing to do with the probability any of the other ones existed. We can't assume any relationship between the data points. And if it's identical, it means they all came from the same distribution. That's governing this. So they've all come from, there's some underlying model of the data, and they've all come from that, right? And we'll give some examples when we talk through this a little bit. But this is good to keep in mind as this pipeline, and this noise is added on often in this process of collecting the data, and then we have to deal with this when we're building the model. And sometimes what you say is this model plus outliers. So there's the core of the model, which is describing our data, and then there's the outliers, which is there's some other stuff floating around. Okay? So before, I think it's useful to classify this noise and these outliers as into three categories, and then you'll treat them differently. Okay, so the first one is just these spurious measurements. Okay, so this would be, it's an R. So this would be the case where, if you have a data set, and if you're entering, a lot of data still, even though there's a lot collected automatically, there's a lot still entered by hand. And sometimes people will hold their finger down on the keyboard and type an extra 6 zeros into something. This still happens. You still get these crazy values which are very far away from everything else. Right? This is if you're trying to fit regression curve, and you have you have your data. It looks like this. You think the data comes from this. This would be your model, this line, and then there's some data point which is way down here. This curve does nothing to explain this data point. It's completely. And this picture, you can see the variation in this data, and you can still see this data point. Often it's going to be the case that you won't even be able to see the variation in this data and this data point in the same picture. It's going to be so far away. It's just ridiculous. If you have this happens in the real world with these automated ways too, where you have, say, some sort of some sensor and it's collecting data, and it might just misfire, right? So it may come back. So sometimes there'll be these like you can think of even on these robots, they have like these laser rangefinders that are kind of shooting up this laser. It bounces back and says how far away is something. They do this with, like, for example, with sonar under the ocean. They're trying to map elevation of the ocean floor. This is really the way they can do it. They can't send someone down there. What happens is sometimes they'll do this with a laser or something pointing down. It'll instead of hitting the floor, it'll actually hit a fish and it'll bounce back up, right? So you get this weird spike in the map of the elevation of the open floor, and you have to remove, you kind of, or somehow deal with these weird data points, which have nothing to do with the actual model. Okay, so this is kind of what's meant by spurious measurements. So another one is just so is just this measurement error, right? So that'd be more like if you're looking at these data points that actually are fit by this model, some of them are not directly on here, right? They don't totally fit the line. If there's no noise, all of the data points would be exactly on this blue line, right? These are off by a small amount. This can happen when you're doing measurements. Your equipment is not precise. If you just have some rounding errors, this will happen. This also happens if you're dealing with very large data sets. Say you're collecting people from data from the internet. You're going to get like if you have these surveys online, like there's now some like so now a lot of the polling for the elections, strangely, this is moving largely to these online polls. They used to do things where people would call up houses and talk to people, and this would be the basis of the polls. And then a lot of people got cell phones, didn't have landlines, so then they're trying to call the cell phones, but the response rates weren't good, and they figured out, well, we can get more data by doing this online. We can send out surveys, and the response rates are less, and it's noisier. But there's some fraction of responses which are not kind of the right, aren't very accurate. But if you look at a poll as a whole, it's going to be pretty close. It's going to be some, maybe it's just the sample you have is a little bit off, right? So this can happen in various forms. It's that when you have each data point is not going to be exactly the model. It may be off by a little bit. This is probably the easiest noise to deal with. This is what we typically think about, and these are kind of these are often like the outliers. But often the boundary between these two, is fuzzy, right? So if you have a data point that was right here, is this an outlier, or is this some measurement that you should actually be using to try and fit your model? It's hard to tell. Okay, so then the third type is like the third type is I try and classify as the background data. So this would be like if you're trying to measure. You said if there was a big if you're measuring the traffic close to the university and there was a football game, right? So there's tons more traffic than normal. How much of that came from the football game? Well, most of it did maybe, but not all of the traffic. There's some normal amount of traffic that drives by the university. And so you have to figure out what is the normal traffic that's not the traffic that you're trying to measure. This could be like if you're dealing with these like this big Netflix data set, right? There's a lot of missing data in here. So it's kind of, this is kind of like that's background data that this person did not rate this movie, right? But there's, you know that they didn't rate the movie. There's something that tells you, but it's not really the phenomena that you're trying to figure out. There's some other stuff going on. Another way to think about this is, say that you're measuring the frequency of tweets, right? And so say this is like the frequency over, this is over time, and this is the height of like the hashtag. What's a popular hashtag right now? Who's the new host for The Daily Show? What's that guy's name?
Bob Ross.
Okay. Well, I don't think Bob Ross is trending right now, unfortunately. So there's there's probably a lot of chatter about the Daily Show because they just announced who's the new host.
Trevor Noah?
What? Trevor Noah. Trevor Noah. Okay. Trevor Noah. Yeah. How about that? Someone so who had heard of Trevor Noah before right now? Right? Yeah. Hopefully he's good. Anyway, so there's probably, for the hashtag Trevor Noah, is probably trending right now, right? So there's this big spike. Now, maybe he had been in hashtags before. Apparently he was a stand-up comedian in South Africa, I think. So maybe when he did some other stuff, there were some spikes here. So you want to figure out how much of this is because of the new post, the new announcement he's hosting The Daily Show, and how much is this background to subtract this out. Right, so this is kind of the background data, which is not what you're trying to measure right here. Okay, so maybe there's someone else named Trevor Noah, and someone was excited they met a new friend and they're going to hashtag them, right? Is that how people use hashtags, right? No? Okay, how many people use Twitter, like actually post stuff on Twitter? No, okay, a little bit. Do people use other things? Use Instagram, Facebook? Is there something else? Like Meerkat? Anyone using Meerkat?
No, I don't use hashtags though.
You don't use...
Yesterday I told my wife, hashtags, they confuse me.
The hashtags?
They're very confusing.
It's like you're counting something, right?
Yeah.
So, okay, so... All right, so are the rest of you are not on social media, or are you? No, so it's okay. So that's fine. So I'm a passive social media. I read it. I read Twitter, but I don't post much. So how many people still have a blog? How many people still know what a blog is? Is this still that's too old? Okay, most of you still know what a blog is, so that's good. Otherwise, I'd feel really old. Okay. Okay. So these are kind of the things. I think it's good. It's good to keep in mind these three types of noise, because when you're dealing with this, you may want to do different approaches to filtering out each of these. These spurious ones are really things that are anomalous and are not very helpful. But the measurement error, you can kind of, it's not so bad, right? Most of what we talked about, we assumed that there was some measurement error, and we're trying to fit a model to it, or we're trying to cluster the data, right? So this model could be linear regression. These could be the centers of clusters, right? If there's no noise in your clustering, you're doing k-means clustering, then there were just three, and it was three means, and there are three different locations the data points could be. That would be easy, right? Maybe the data each has its own distribution, right? And so maybe this measurement error is within the distribution of the data. But that still makes it trickier than if it was all at a particular spot, right? Okay. So I'll talk about some ways of dealing with these, and in particular, trying to detect these outliers, or sometimes these are known as anomalies. And the anomaly and outlier, sometimes these are kind of things which are just wrong, and you just want to get rid of out of your data, right? But with sometimes these are interesting, right? This if you were tracking the hashtag Trevor Noah, then then today, there'd be a big spike, and this would be meaningful that you found this, right? So it is, sometimes you want to identify these things. Okay. All right. So, okay, but before we move on to how to deal with this noise specifically, I want to there's another topic that I want to spend some time on today that's very related to dealing with this noise. And this is cross-validation. And I've been discussing this. This has been brought up in lectures, several times already. But I just kind of want to make this more formal, what's going on here, right? And so this is because when you're dealing with outliers or you're dealing with data mining, so most models have most models have some parameter in them. Sometimes this parameter is kind of implicit, right? But and if you're dealing with noise and outliers, I claim you basically always need some parameter that kind of tells you when something's an outlier and when it's not an outlier. And we'll kind of revisit this a bit later. But so so k-means clustering, then this parameter is k, right? So if you're dealing with lasso, then what you're minimizing is ax minus b2 plus s. I changed all the notation for this, but maybe this is times s1, right? And so here, this parameter is s, right? So there's some parameter here, right? So if we're dealing with PCA, what we do is, what we often use this for is the best rank K approximation. Call this matrix AK, and then this parameter again is K. You're saying some dimensional subspace to keep. The rest of it, you're saying, is kind of noise, right? The model is the best rank K, and so there's this parameter here in K, right? And we talked about with the k-means clustering, there need to be some way to choose this, and I said, well, there's this technique based on this elbow technique where you can plot as a function of k, you have some cost function, and often what happens is the cost is decreasing as k, and it kind of plateaus, and then so you choose some, say this is the elbow, and so you choose this value k. Whereas if you increase the number of clusters, it doesn't decrease the cost that much anymore. This is kind of okay. So clustering, you often don't know something about the data. For the cross-validation, you'll need to know a little bit more in order to use that. So that's why this may not directly apply with all k-means clustering unless you know more about your data. Or you'll have to rig something up so this can work. Another important one, and hopefully if you're in machine learning, you're discussing some stuff like this. But if you're doing polynomial regression, right, then there's some degree of the polynomial. So then what you do is you fit the best polynomial curve instead of this linear curve, and so then this parameter is this degree of the polynomial. Right, so if you make this degree too big, you're gonna get all your data exactly, but you're gonna be overfitting, and this is not going to generalize very well. Okay, so there's always some parameter, and we want to figure out how to choose this parameter. Okay, so how this is typically done is that you think of your input your input data set is P. And so what you're going to do is you're going to take some subset of this data. So it's not necessarily these consecutive blocks. And so this would be, say, you're going to take this subset to be Q. Do I have this? All right, let me switch this so it aligns with my notes a bit better. So this subset to be R, and you're going to take this out, and then everything else was left over. This is going to be Q. Okay, and so you're going to have it so Q union R equals P, and Q intersection R equals the empty set, and this split, and it's important that the split is going to be random. Okay, so you're randomly going to divide this data set into two parts Q and R, and so this Q is going to be the training set, and then the R is going to be the test set. Okay, and so then what you end up doing is you're going to so you're going to build a model M, and it's going to be built on the training set with some parameter, and let's call it K here. And then you can evaluate, so say some cost of M, say QK, on the test set R, right? So if I evaluate how well it does, right? If I evaluate, I have some cost function. So think of the k-means cost function, the sum of the squared errors from all the centers. You find the centers using the data set Q, and then you measure the cost on R. Is this clear? Do I need to rewrite it, or can you read that? Okay. So what is the advantage of doing this? Why would you want to do this?
Kind of get absolute results in a small piece and really know, rather than kind of guessing over large pieces.
Yeah. So it's not quite an absolute result, right? An absolute result. The right way to think about this is to go back to this picture, right? Mu x and mx. In this case, I changed x to p. Okay, this was our input data p in this case, right? At absolute results, we'd have to know this data set mu. Okay, but all we have is this is x, or this distribution mu. This may be continuous, maybe way bigger than x, something like that. So we don't quite know absolute results, but it's kind of on the right track. This is somehow going to be better than evaluating on Q, right? So this cost would be, so let's say this was k-means, right? So then this would be, this M was going to be equal to, say, C1, C2, C3. So this was actually this set of centers. Okay, so this was the model, and then the cost was going to be the sum over all the data points in R times the distance, say, from P to phi of C of P, say, squared, right? So this would be the k-means cost, but now C was determined entirely by the data set Q, and P is only over the set R, right? And we could normalize this. We can make this 1 over the size of R, right? So then it didn't matter the size, right? So why is this better than measuring on data set Q? Why don't we evaluate the cost on the same data set that we built this on? Yep.
So things attributed to the model will appear in both sets, but things that are noisy, like outliers, will only be in one
And so,
Yeah, that's right. That's good. Great. So if you have an outlier, right? So think back to the homework. There's one data point that was far away from everything else, right? That data point is either going to be in Q or in R. Okay. So let's say we built the model. So let's say usually Q will be larger than R. Is usually how you do it. So let's say it was in Q and built a model that included that outlier as one of the centers. And then we calculated this cost on the data set R, which did not have that outlier. Well, this data set, the cost is going to say, well, that outlier was really silly. I never used that. I never mapped any data point to that center. That was kind of silly. That wasn't very useful. And that's because if often that data point, if it was an outlier, you shouldn't use that to build your model, because that's not going to generalize to new data. So the whole point of doing this is to generalize. Okay? And so the idea of generalizing, if you go back to this picture, we want to build this model so it captures mu, not x. Right? We only have access to x, but we want to capture mu. And we assume that data is coming independently and identically from mu. So generalize is the idea that if you have new data from mu, you want the model to do a good job. The outlier is not likely to be similar to the new data. So you don't necessarily want your model to capture that. If the outlier is likely to be new data, then you do want to capture it, right? So you kind of need to decide whether it's an outlier, whether you trust that or not, right? But if there's only one of them, then maybe it's not that important. Okay, so it's this idea of generalizing to new data. So you want it to work on new data so that so that, like, if you're building a model, like if you're Google and you want to have a model to which web pages are popular, you want so when someone comes back and searches again, they're going to find the right results. You don't care if old people liked it or not. Those people aren't searching for that anymore. You want to care about the new experiences. That's often the point of building these models. Okay, so this cross-validation is really important. So the other thing is that it will. So one is that this will generalize. The other is that we had this parameter k. Well, maybe if we use this correctly, we can actually figure out how to choose the right parameter k. How would we do that? How could we help choose the right parameter k using cross-validation?
Just run multiple cross-validations and see if with different values in k, and then kind of plot and see the pattern. What looks like what gives us the lowest error in the verification?
Yeah, so we can do something like, so the simplest thing is just setting k star as the arg min over all values k of the cost, say, of some model that's built with some training set q and a value k and tested on the test set r. That's an r, right? So now this cost is now a function of k, right? It's so now I can find the k that gives me the best cost, right? If I did this elbow technique, then what's happening is the cost is always decreasing as I'm increasing k, right? If I did PCA, the best rank k, well, if I said k equals to the dimension of the data set, then that's going to give me the least error, right? If I do polynomial regression, I can set the curve, the degree as high as I want. I'm going to get 0 error on this, right? But if I'm doing it on this training and the test set, that will no longer be true. What's going to happen instead here is that you're going to have some curve, and it's going to look kind of like this. Well, probably won't go up that high, but it's going to come and it's going to have some minimum value k that is, if you have a k that's larger, what you're going to do is you're going to have these data points which are not necessarily useful as the centers of the data. For clustering, maybe this isn't the best example, but this is definitely the case with regression, right? If you do this lasso or you're doing this ridge regression, you think of ordinary least squares. You're just implicitly setting the S term in the ridge regression to 0, right? So you're always setting that to 0. If you're doing ridge regression or lasso, then there's some other value of S that you can choose. And what's going to happen is there's going to be some value S which is going to do better on the test set than setting it to 0. So you'll do this as part of your homework. So you'll run regression, the ordinary least squares, and the ridge regression, and you'll break it up in a specific way into training and test set, and then you'll find the value S which is doing the best on the training set. And it's not going to be the value of S that's where you set it to 0. Okay, so this is maybe a little bit surprising, right? But it's because there's noise in the data. And if you try and fit it too carefully, you're going to what's called overfit the data. And this helps you to not overfit the data. Okay, there's still a third reason why you would want to do this cross-validation. So one is that it's going to generalize better if I somehow predict if I can set my parameter value so that it is based on the training set, it's based on the error in the test set instead of the training set, this is going to generalize to new error better. And that's because I can assume that both Q and R, because I've split them up randomly, are both IID. So then Q serves like a perfectly reasonable training set. It's just a little bit smaller. So maybe Q is 90% and the test set is 10%. And then this test set data is also IID. So it looks like new data coming from the distribution mu. So that's why it works. Okay, but what's another reason why I'd want to do this other than choosing my parameter value? What else would I want to choose, make a choice over that this would help tell me? So a lot of you are doing this in your projects. You're comparing a few different algorithms. So if you have different algorithms, right? So let's say that you're trying to, you're doing different clustering algorithms, and you somehow have some maybe they're computing different cost functions, right? Or maybe you're doing spectral clustering versus k-means clustering. You can compare them. You can train on one data set and you test on another data set. It could be that sometimes spectral clustering will give you better least squared errors than k-means, than like Lloyd's algorithm will, even though they're optimizing things which are separate. But if you do it on the only measure on the training data, then k-means is always going to do better, probably, or almost always do better. But if you train on separate test data, the spectral clustering might end up doing better. Or you could use a third cost function, right? A different way you could use the k-median cost to compare k-means clustering algorithm like Lloyd's versus spectral clustering algorithm. But again, you'd want to do it on this other test data. This is a more fair thing. So when you're kind of comparing things and trying to see how they generalize, comparing them to different algorithms, you also want to do this cross-validation. Okay, there's one tricky thing, I want to talk about. There are these contests out there on the web. There's like One of the most famous one was this Netflix contest where you could win $1 million. There's also this site that's called Kaggle, which has all these kind of data mining, machine learning challenges out there where they have a data set. And basically, how they've done it is they had some initial data set P, and they broke it up essentially randomly into 3 parts. Okay, what they've done is they have some first part of the data, Q, and they give this data out. So this data is public. Okay, then they have another part of the data set here, R, and so this is the training. But this is not public. What they do is they allow you, or they used to allow you to submit some model or some classifier or some sort of structure to their servers, and they would evaluate this for you. They would evaluate on the training data. And then they have a third data set. And so this will give you the final score is measured on this data set S. Okay? So why would they break it up into these 3 parts? Why do they have a third part for the final score? Yeah?
So you couldn't tune in, kind of hype up your engine or whatever, so that this would run under all situations.
Yeah, right. So, even though you don't have full access to this training data, and they usually have a rule you can only submit a new kind of classifier only once a day. But still, you can do this over the length of these contests. You can usually do this hundreds of times. You can submit hundreds of these different checks, right? So if I had some model in my parameter, I can submit 100 different choices and then return the best one. If you're in machine learning, there's a technique called boosting. And so what you do is you take a bunch of weak classifiers and you combine them all together. And you kind of need to know which ones are working, which ones aren't, and you can put them all in the training set, and that tells you how to combine them together. But these can be completely random classifiers. Combine them together will do really well on the training data set. But it won't generalize necessarily to this final score on the test data set. If you use this R as part of your training procedure, then you can't also use that to predict how it's going to generalize. Right? So if I go back here, one thing is all I was doing was comparing different algorithms. Then this is fair. I can use just Q and R. I didn't use Q to determine each of these algorithms. But if I used Q and R already to choose the model, choosing this value K or this value S, and if you're using there's a whole class of these Bayesian techniques, for instance, where your model can be much more complicated and you're interacting with the data to choose a much more complicated model, then you can use R to really tell you which whole model to pick. It's not just this parameter, but there's a lot more that can go on in there, right? So if I'm using R to do that, then it's not fair to compare against on R also. You need a third part to do the final comparison. Okay, so it's important if you use R to choose parameter, then you need, or you use this somehow to choose your model, then you need a third part to tell you how it's going to generalize and to predict how it's going to do on new data as it comes in. Okay. So any questions on cross-validation in general? I mean, it's a really, to kind of know how things are going to work, to know how well this is going to generalize to new data, not to be overconfident in your predictions, you really need to use this, right? This is kind of a really important thing to use. It's often, sometimes, it's kind of unspoken that you would need this at some point, but I really want to stress that you should really do this to make any sort of prediction. And there are still lots of fields out there, lots of parts of science and engineering that are implicitly not doing cross-validation. They just kind of build a model and they don't know if they're overfitting or not with the data. So it's always, there's a lot of parts of science that really need to be reevaluated to think, are they doing cross-validation? I've talked to other professors in other departments in campus, and when they learn about cross-validation, they're like, wow, this is really important. So I hope it kind of, don't forget to do this when you get out in the real world or if you're already there. So mention a couple things. So often, you'll do things where like Q is like, say 90% and R equals 10%. This would be maybe if your data is not too big, you're doing it once, this might be a fair thing. If your data is really big, you might make R smaller. You don't necessarily need a huge training set or test set to really validate how well it's doing. But if your data is small, you want to put as much into the training set as possible. So what people will often do is leave one out. So this is LOO, or leave one out cross-validation. And the idea is for all P in the data set QP equals P set minus P. Okay? And then by doing this, if your data set is of size n, you're going to get n different sets of training data. And the test data then is the single point, right? So you leave one data point out, train the model, and then test on the single point, and then you can average over all these values, right? And then you want to average over the cost on, say, M of QP tested on the value P, right? So then this would be what you would evaluate. Now this can be kind of slow because you're doing n times as much work. So if you have a much larger data set, you usually don't need to do this. You don't necessarily need to do all these different things. But if you have a smaller data set, every data point is precious, so you kind of want to put as much in the training as possible. So another thing that's worth mentioning is there's a related technique that's called bootstrapping. And so the idea here is to choose Q with replacement from P of size, the same size as P. Okay, so what I'm doing is I'm generating a training set that's the same size as my input. Okay, it's the same size as the input. Now, if you don't do this with replacement, then you're just going to get your input back, right? But if you do this with replacement, that means you can pick some points twice. Okay. So why would you want to do this? Why would you want to choose a training set with replacement from P? Why does this make sense to do? When this was first proposed, this was proposed by Efron in like 1979, and people are very surprised. They're like, I don't know why you'd want to do that. It seemed it was a very strange concept. But what are the advantages of this, or why does this make sense? What can you get out of this that you can't get out of these kind of training and test sets, or this leave one out? Yeah?
You might get a shape of the population distribution.
Yeah, if I assume it's IID, I can kind of get that from a sample Q. Q is like a sample as well.
You get more data?
Yeah, so one thing is you get more data. I mean, if I wanted to, I could sample of size 2P. Right? That'd be even more data. It turns out that of size P is interesting because it tells you what your data predicts. Right? So I'm sampling with replacement. So if you go back to this, I want to sample IID points from mu and build my model on that. But I I kind of have access to X, and X I assumed was IID, but if I want to do this, repeat this process with random trials and kind of average them, I can't sample more IID data from you. The best I can do is I sample IID from X. So if I'm sampling with replacement, that's essentially sampling IID from X. This gives me a Q, and so this is the bootstrap. So it tells me if I have n data points, IID from whatever distribution this is from, how good of a model can I learn? How stable is that model? So what you would do is you would go and you would sample these Q with replacement, and you can do this multiple times. And for everyone, you build a model, and then you look at the distribution of these models. Right? So instead of building, so if I can draw a picture here, right? So if my data set looks like this, and so instead of just building one classifier, for instance, if I have one outlier point and I use the ordinary least squares regression, then sometimes if I sampled this one, my regression curve may come down like this. Sometimes it's down here, and sometimes it's through here. All right, and so I'm going to get, yeah, I know these are supposed to be straight lines. I'm sorry. Let's pretend this is order 3 polynomial regression. Then I think those are okay, right? Those look like third order polynomials. Maybe? Okay. But you'd get some variation here, and it would depend whether you sampled an outlier or not. You say, so how stable is this choice of algorithm to create a model? Well, I can do this bootstrapping and do it multiple times and look at how stable these results are. If they're all really the same thing, I know, okay, this algorithm was really stable with the data. If I ran, if I ran the lasso instead of the, or if I ran some form of ridge regression, and it was much more stable than before, and there's ways of measuring the variance of these things, then I know that's probably a much better fit, right? Because if this data really was IID, I shouldn't have trusted this one data point so much. But say if there were 4 of these data points right here, then probably on most of the samples, I'm going to pick at least one of them. So the model should always be down there to some extent, right? So it'll kind of tell you about how stable your result is on this data set. So that's why you do it of exactly the same size. It turns out if your data set is large enough, you're going to get it. Turns out you get like 66% of the distinct data points on average. And there's kind of some really cool new stuff where people have said, well, on really, really big data sets, this became possible in '79. They started doing this when they first got computers and stuff, and these were like probably on punch cards back then. I don't know, 79 might be. I'm not sure what they're using, but this was really at the beginning of computers. They're like, what can we do in statistics with computers? So now the data is so big, even this is often not feasible because the data sets are so big, and more so than you can't really parallelize it because you end up having to copy the data over a bunch of times. So people have said you can actually sample sample a smaller number of data points from P and then bootstrap on that with the same size as N. But because you're doing with replacement, the size of the distinct items never goes up so big, and you can kind of replicate this analysis. So there have been ways that even making this up so you can highly parallelize it. And there's a lot of cool stuff here. There being these big systems built that allow to kind of get early estimates of big data by using ideas from bootstrapping. So it's a really powerful technique. But I just want to give a picture of how it fits in with the rest of cross-validation. Okay. All right, so let's go back now. Let's go back now and talk some more about these outliers. Okay, and I want to ask the question: when is a data point an outlier? Right? How do you know when a data point is an outlier? What's the right way to kind of formally do this? And so basically I'm going to argue that this process basically needs some magical parameter. And unfortunately, often this is the sort of parameter that you can't cross-validate to figure out what the best one is. Because you often don't have maybe you can do something with bootstrapping to try and figure this out, but you often, there's still going to be some parameter built in there. And I'll try and kind of demonstrate this throughout the next part of the lecture. That it's almost impossible to avoid. There's some stuff with these density-based clusterings or density-based approaches that people claim doesn't have parameters, but it's really hidden in there somewhere. Okay, but aside from this, how would you do this? It turns out that there's a fairly kind of the right way to do it. Almost always fits in a certain pattern, right? So the first one is you're going to build a model M of your data set P. Okay. Then for each data point in your data set, you're going to calculate you're going to calculate a residual. We'll call this RP, which is some distance from the model to this data point. So this is often associated with the cost. This may be depend on the cost. This may be like with regression, this was the vertical distance. With PCA, it was the orthogonal distance. With clustering, it's the distance to the nearest cluster center. There's some way of measuring the distance from the model to this data point, right? And then you're going to say, if RP is too large, it's an outlier. Okay. Okay. This seems very, very simple, right? And kind of, it's kind of obvious. But almost every technique you see out there somehow reduces down to this. You can somehow write it in this formula, where you're building some model, you're calculating these residuals, and then you're throwing weights out. And this what the model is, what the residual is, that can change. And then there's always this too large notion. There's some parameter here that says whether it's too large or not. And at some point you need to make some decision. Okay, and this is kind of unavoidable. There's some models that claim not to have a parameter, but that's probably because really there is a parameter, but it was by default set to 0 or 1. Like if you're doing least squares, it's really ridge regression with the parameter set to 0, right? So there's a lot of, so if you see that it doesn't have a parameter, think about it hard. You can probably fit in this model, and there's some default parameter. But the reason for this is because there's no right answer for what the parameter is either. There's this gray area. I drew that picture. If I have this data set here and I fit some model and I have a data point here, is this an outlier? Is this data point outlier? Maybe if it's way down here, sure, it's an outlier, right? I believe you. But if it's right here, I'm not sure. So it's kind of, and there are lots of, so like it's another thing of why this is hard to tell is if you generate data. So let's say all this data, all my data is IID from just a normal distribution. Okay. A lot of data out there is generated from normal distributions. People's height is pretty close to is pretty close to from a normal distribution. If you factor from men and women, or you normalize to various populations, right? At what point is someone an outlier as being tall? Maybe it's the point where they need to shop for clothing kind of differently, or something like that. But these are arbitrary cutoffs. If you look at normal distribution, we know that this is centered around 0, and we know that one standard deviation, 1 sigma, out to here, this is going to be, so you're going to have about, in this range of 1 sigma, and in this case it's 1, a distance of 1, the amount of data in here is about 1/3 of all points. So if you said outside 1 standard deviation, you're saying 2/3 of the points are outliers. But they're all from the model. None of them were kind of these spurious things. If I go out further, if I go out to 2 standard deviations, 2 sigma, then this is going to capture, so 1/3 of them are outliers. In this case, it's 1/20th of the points are outliers. Right? So if I generate 20 points, probably roughly 1 of them will be an outlier. But it's still from my data. I can still say they're all reasonable data points, right? And you can go on. Even if you go out to 3 standard deviations, then it's going to be something like 1 out of 300 points. But if I have 1,000 points, I'm going to have some outliers, but they're just from a Gaussian distribution. And 4 sigma is like 1 out of, I guess, 1,600, or 16,000. Right? There's no cutoff where it's different from being from the distribution or not from the distribution. Right? So how do you know from any individual point this way? But versions of this process. So if you look at this process, there are some versions that work better than others. Right? There are a couple things to try and optimize here. So one is to make this choice of too large. You want to somehow make this so this choice is going to be somehow intuitive, right? You want to make it so you understand what this parameter means. So maybe the k and the k-means clustering, maybe that makes sense. If you're doing like a polynomial regression, I don't know what the degree of the polynomial means. Maybe this is intuitive. If you're factoring based on a distance, you're saying this residual is actually the distance here. You can say if my prediction of someone, say I'm predicting someone's income based on what school and where they grew up and something like that. If this is off by some, maybe it's going to differ in different parts of the data for different income class ranges, right? But it could be that if this is off by some quantity like off by $1 million, then that's some quantity that actually makes sense, right? That you can put some numbers to, right? So if you look at like someone like 50 Cent, right? Grew up in a bad neighborhood, right? And became a millionaire or whatever by rapping and so forth, right? He may, based on where he grew up and the education he had access to, he'd probably be down here, but he would be an outlier up here because the difference may be like $1 million. That's something you can intuitively understand what that means. So if there's a parameter, you can make it so it's more intuitive. So that's one thing where you can kind of choose to optimize this. The other is when you're building this model, you want to make this part so it's already robust to outliers. Right? So actually, if your model is robust enough, if your model is insensitive to outliers, say you're doing, instead of regression, you're doing something like I talked about this Thiel-Sen estimator, right? That was like an extension of the median to the notion of this regression. That's already not going to be affected by outliers. So maybe this model itself, if I already have the model, then maybe I don't care about outliers anyway. So all I care about is the model. If you choose a good model, then this process is easy. It's more stable to throw away. Like you can probably be more sure that these are outlier data points under, how you've chosen what your model is supposed to mean. Whereas if you do this if you use least squares, it could be that you threw away data points which are actually the core part of the data because you were fitting it towards outliers. You may be throwing away the wrong points. But if you build this first to be robust, outliers are easier to identify, and maybe you don't even need to identify outliers. Sometimes you might want to first build like a Thiel-Sen estimator, maybe even on a sample of the data, identify outliers, and then go back once you've removed those and use some version of least squares. Maybe that's better. The first round, maybe you do this in rounds, and the first round you use something more robust, and then the second round you do something that maybe has better error in terms of your cost function. So you can think of mixing these things up. And it's okay to kind of repeat this process. It's okay to think of having some loop that goes through here where you remove some outliers, you go back and build the model again, and then maybe you remove some more. But you have to be careful. If you say always, there's some silly things you can do that don't make sense. Always, instead of a distance too large, you can say always to say 10% of points are outliers. So if always 10% are outliers, eventually you're going to have no data points left. So actually at some companies, what they do is they have this policy called the Lake Wobegon policy, where every year they let go like the 10% weakest of their employees, so then everyone is above average. But then they hire new employees, so and ends up that's how they stay as a company. So you have to somehow inject new data into this. But maybe you could hold data out in this model or something like that. Okay, so one other thing you can do. We talked about this. Yep.
So, do you assume like outliers shouldn't be a lot, right? Like, do you assume outliers should be like less than 1% of the data, or do you assume something like this?
Yeah. So I haven't said anything to assume whether they're small number, right? So there are these forms of these robust estimators. So it's like if you're using the median, it's robust up to but not including 50% of the data being outliers. Okay, at the point where 50% of the data are outliers, you probably don't have a single point that describes your data very well. There's probably something else going on, right? So there are these notions that generalize up to a huge amount of the data could be outliers, but typically, if you have that much of your data, it's no longer outliers. It's no longer something you should be ignoring. This kind of gets into this background data, right? So that kind of is a different sort of thing. Actually, this brings me to a good another topic. Where did I have this in here? Yeah. So. So one part where this comes up is often in data, especially in data when it gets really large, you'll find that you have what's called a heavy tail. If your data may follow a heavy tail distribution, right? So if you have a Gaussian distribution. Right? If you look at this, so if a data is x is from a normal distribution, then the PDF of x is equal to e to the minus x squared. Essentially, this needs to be normalized and so forth, right? But if this means that as x gets far away from 0, the probability of it being out there drops off exponentially, right? So this would be like a light-tailed distribution. If I drew a picture of this, it's going to be, something like this. Where if I get out pretty far, I drew that picture before. You said there was some probability of being an outlier, but out here it's pretty much basically 0. This is almost up to measurement error. The probability of being out here, if you get out maybe 6 standard deviations, is basically 0. Right? It really drops off really, really quickly. Where this is the domain of X. Right? But there are other notions, these heavy tail distributions, where it does not look like this. So this is not heavy tail, just so that's clear. Okay, so this happens, especially we'll talk about graphs in the next part of class starting next week. And graphs are often have these distributions of the degree of every vertex is often not that distribution is not heavy-tailed. Is heavy-tailed, and that you'll get a lot of people who have a very small degree and a few people with very large degrees. Another popular example is this is the zip distribution, and so that is so if you look at frequencies. Remember, like from the word count thing. So if you look at the frequency of the word of the ith word, this is going to be roughly is going to be some constant times 1 over I. So now this is decreasing as say I have them in sorted order. The most frequent one is word 1. Then that means as I get out to further words, this is decreasing polynomially, not exponentially. And so it turns out the word use in the English language follows pretty close to a zip distribution. So the frequency of the word the is about 0.07 in a lot of corpuses. Right, I've got some other stats here. The frequency of the word of is about 0.035, and the frequency of the word and is about 0.028. Okay, and so if you look at these first 3 things, so these are the 3 most popular words in a lot of large sets of text. Now, if you look at Twitter, maybe this is different. These are from like books written. So I don't know who reads books anymore, but so in this, now it's probably hashtag or something, right? Is the most popular word. But so if you look at that, this follows where C is actually 0.07 in this case. The first 3 words follow that almost perfectly. And so you get this smaller decay, but it means there are lots of words out there. Like if you look at word ranked 1000 and 1001, they basically have the same frequency. It's very flat as you get further out. And so in this case, you have a lot of points that could be outliers. Right? And I was discussing with I don't know if he's here before class. So there are these techniques used by in kind of some part of natural language processing, although NLP people will sometimes deny this is part of NLP. There's some like rift in the community for various reasons, but so there's this notion of a topic model where you can look at these sets of documents and kind of cluster them, or you try and cluster them based on topics based on the word frequencies. And these clusters are known as these topics. And you can build this topic model, which is like a way of understanding all these sets of documents based on the sorts of words used in them. There are a variety of ways to use this. There's something called latent semantic indexing, which is a simple one. There's LDA, which is latent Dirichlet allocation, maybe. There's 2 LDA. I always mix them up. But anyways, there are a couple of strategies out there with different acronyms. And to get these to work well in practice, what they'll do is they will often they will drop words that are occurring 2 times or less from these models. But this may be 30% of all words, right? So they may be dropping 30% of their data set because in the algorithms it only occurs twice. And then the algorithms just don't know what to do with that. But there's 30% of the words may occur 2 or fewer times. And maybe it's not a 2, maybe it's like 5 or something. There's some small constant number or threshold they throw away, and that can represent up to 30% of the data. I mean, it works well in practice for various things, but it only has certain level of resolution. It never can really explain too much of the data. On the other hand, so this is one model where they say, well, these are outliers. I'm going to throw them away, and they can still do all right. But all these small occurrence words would screw up their models otherwise. But on the other side, a lot of the kind of the business of the internet has been built on exploiting the heavy tail and exploiting the outliers. Okay, so really good example I like to use is if you look at the company like if you look at the company Amazon, right? How did they get their start? Was in selling books, right? So if you look at Amazon, so if you are a bookstore, you can maybe carry 10,000 books, right? Popular bookstores, when 15 years ago, would carry maybe 10,000 popular books. Amazon came along and said, we can carry easily 1 million books. Maybe it was 10 million books. Because, you know, if there was some book that 1,000 people would buy, then they could order 1,000 books, keep it in their warehouse, and send it out as cheaply as any of the other books. But a bookstore couldn't do that. If there are 10,000 people in the country that would buy it, well, if you're maybe in like New York City, then maybe 100 of those people live there, and so you can exist, right? But if you're in some smaller city or suburb, people don't want to go all the way to a bookstore. They'll just buy it on Amazon. It's easier. And you can search and you can do all sorts of other cool stuff, right? But this kind of put a lot of these bookstores out of business because they could only keep so much on stock, where Amazon could cater to this heavy tail or this long tail, right? And now 10 million, you know, they can do much more because they can either print on demand or they can have it just electronically installed on the Kindle. Now all it costs is the space on a hard drive, right? So they can cater to even longer the tail. And so they're actually doing this again now with doing like stuff for TV shows. They're making these niche TV shows which appeals to maybe 10,000, maybe 50,000 people, but they're very dedicated people, and then they can serve very targeted ads to that group of people, and you know it's still profitable. So by exploiting the heavy tail, you can get a lot out of this data, and so you should keep in mind, if you're going to be throwing away outliers, you need to think, is this a light-tailed or a heavy or long-tailed data set? And it may change your strategy. So I think we're out of time here. I think I said most of what I wanted to say about this. There's some other commentaries in the notes if you're interested. On Wednesday, we'll talk about a thing related again to noise, and you may not realize what this is related, but instead it has to do with privacy in data. And so we'll find out about how these related again on Wednesday. So, great.